Yes, yes.
That was bugging me, and I thought, I know what it is. Like I said, the masks don't help. You guys see that okay, or would it help if I turn the lights down? It's fine. Okay. All right. I'm afraid if I turn the lights on, you'll like fall asleep. Okay, we'll go ahead and get started. Can the people on Zoom see the test results and then hear me okay? I'll try that again. Can the people on Zoom hear me okay and see the screen?
Yes.
Yes.
Thank you. On the edge of my seat there. Okay, so in general, I think people did pretty well in the exam, so congratulations on that. One thing I was pleased about was on the quiz, we had the one where you had to calculate the total heat, and I think people kind of struggled with that on the quiz. I did see an improvement on that on the exam. We had the 2 questions that were similar to that. So once again, if you improved on that, congratulations. If you didn't, take a look at it again, because something like that is most likely going to wind up on the final. That's kind of a classic heat flow type calculation thing that is pretty commonly done. And so you may see that again on the final. So what I'd like to do today is I'd like to go through the exam and go over the answers. And if you have any questions or anything, please ask, and I'll try and answer the best I can. And then after that, we'll move on to chapter 13. And so we've been talking about solids. And so now we're going to go and start talking about solutions. And so we'll work on that the rest of the class today and then on Tuesday of next week as well. So, okay. So question 1, which of the following compounds can participate in hydrogen bonding? And the correct answer was the CH3 and H2 and CH3OH. The reason why the one with fluorine is not, so the CH3F, is that the fluorine is bonded to the carbon and the hydrogens are bonded to the carbon. And you can tell that by the way it's written. So there is no hydrogen bonding going on there. Number 2, metallic material that is composed of 2 or more elements is called an alloy. Number 3, the predominant intermolecular force in water is hydrogen bonding. Remember we talked about how you have the oxygen and you have the hydrogen bonded to it, and you get that partial negative on the oxygen, partial positive on the hydrogen. Number 4 wants to know for germanium, what shows that it's a semiconductor based on the gap between the filled lower and empty higher energy levels being small, and that's that molecular orbital model. Number 5, which of these statements about viscosity are true? It increases as the temperature decreases. It increases as the molecular weight increases. And it increases as intermolecular forces increase. Well, in this case, they all are true. And it all gets down to those intermolecular forces. As you have more intermolecular forces going on, the viscosity increases. So that's kind of the common theme. Number 6, the critical temperature and pressure are given for CS2 as 279 degrees C and 78 atmospheres. And then it wants to know what exists. And so if you're at those critical temperatures and critical pressures, basically you have to, if you're above those values, then you have supercritical fluids. So it was above and above was the correct answer. Number 7. Sodium chloride crystallizes in a face-centered cubic cell. What's the total number of ions, Na+ and Cl- that lie within a unit cell? The correct answer was 8. And I believe this was one of the homework problems. So if you remembered it from homework, or if you did the homework, then hopefully you remembered that and got this correct. And so the chlorine, you have 8 on the corners. So 1/8 times 8 is 1. You have 6 on the faces. So 6 times 1/2 is 3. So a total of 4 chlorines. Sodium, you have 12 on those edges. So there's a 4th there, times 12 for 3. And then you have 1 in the middle. So coordination number for each is 6. And like I said, that was taken from the homework. So hopefully you got that one right from doing the homework. Number 8, some things take longer to cook at high altitudes than low altitudes. Why is this? The answer is water boils at a lower temperature at high altitude than a low altitude. Anyone know why that is? Remember what we said about that? It's based on the atmospheric pressure, and atmospheric pressure is lower at the higher altitudes. So that's what that links back to. Number 9, an unknown metal crystallizes in a primitive cubic unit cell. The length of the unit cell edge is 2.85 angstroms. What's the radius? The answer is 1.43. So basically what you needed to do was take that value and divide it by 2. Somebody at the last class was asking me about that, why you didn't use one of the formula that was in the homework problem. And the reason why is the geometry in the homework problem was different than this. For this, if you go back and look at the diagrams in the book, I don't have the book with me, but they show pictures of this. For this simple cubic one, the 2 molecules or other atoms literally touch up against each other. And so that length is simply half of 2 molecules. So half of 2 molecules gives you a whole molecule. The radius then is half of that. So that's why you just take that value and divide by 2 rather than use one of those other formulas. The problem, homework problem we did was a different geometry. And so in that case, the 2 didn't butt up against each other. There was a little gap there. So that's why you had that calculation to do that. So this was actually easier than the homework problem because you didn't have to fool with that. Number 10. That's where we have ethanol, and we want to know what's the total energy to convert 25 grams of solid ethanol at -135 to liquid ethanol at -60. So let me go to the back here where I have this worked out. Let's see. So in this problem, this is what we were talking about before that we had on the quiz before. And it's thinking about what's happening to the material at the different stages, okay? And then using the information that you're given in terms of the constants in that to do the calculations for each step. For me personally, on these kind of problems, the first thing I like to do is just calculate the molecular weight of the compound, because I know I'm going to need that, because I'm at some point going to need to have it converted into moles. And so up on top here is my calculation of the molecular weight of the ethanol, and that's 46 grams per mole. The next things I have written down here, just reminding myself of what we're doing in terms of what temperature does the ethanol melt, some of my constants that were given, things like that. So then I'm ready to start the problem. I got everything set up that I think I'm going to need to solve the problem. And the first step is I had -135 degrees C. And I need to go to -114 degrees C. Because remember, we said that it melts at -114. So I need to calculate my delta T. And there were a few people who got, I think, a little confused with the delta T, and they used negative signs and stuff like that. For delta T, it's just a difference. So think of it as you want the absolute value of that. So the delta T is 21. 25 grams is what I started with in terms of how much material. I have my constant here. That's specific heat of the solid, 0.97 joules per gram Kelvin. And so if I set it up like this, I see my Kelvins cancel, my grams cancel, and I'm left with a value of joules of 5,009 or 0.509 kilojoules. Because eventually I'm going to need to express the final answer in kilojoules. Then the next step is, so I've done that, calculated the energy for that temperature change. Now I want to calculate the energy associated going from solid to liquid. So now I have to use my 5.02 kilojoules per mole constant for that. And here's where I'm going to use also my molecular weight that I calculated in the beginning. So 25 grams, I switched that to moles using that molecular weight. And then now I can cancel out the moles and I get a kilojoule value of 2.73. Then the last step in this kind of path is going from -114 to -60. There, my delta T is 54. And so similar to that first calculation I did, I'm going to now use the 2.3 joules per gram kilogram, gram Kelvin constant. Multiply the 25 by that, and I have my 54K delta T, and I get 3.105 kilojoules. I add all those up and get 6.34. So once again, the key on those kind of problems is looking at what constants you have and making sure you're using the right constants. Take advantage of the dimensional analysis of using the units to know what you should be multiplying by or dividing and things like that. You know you're going to need the molecular weight at some point, so go ahead and calculate that out. Be clear that when we talk about delta T, it's really the absolute value that we're concerned about. So don't put a negative sign or something like that on there. And then the final thing is make sure that you're either working all in joules or all working in kilojoules, because at the end you want to add up and then get things in kilojoules. That can be a little tricky sometimes, and I don't know why this is the way, but you know, this constant is in joules, the top one is in kilojoules, so you just got to be aware of that. Any questions on that one? Okay, so let's take a look at 11 then. Okay, so in 11, it says that a solid has a very high melting point, great hardness, and poor electrical conduction. What kind of solid is this? The answer is covalent network. When we think of this, high melting point, great hardness, things like that, the example that we talked about in class was a diamond. And so that, if you remembered that, that was a covalent network type of solid. Okay, number 12. The unit cell with all sides the same length and all angles equal to 90 degrees. It has lattice points only at the corners is called, that's a primitive cubic. 13, what fraction of the volume of each corner atom is actually within the volume of a face-centered cubic unit cell? That's 1/8. 14. Crystalline solids, they're the ones that have order, so they have ordered structures. 15, cesium chloride crystals in a unit cell that contains cesium plus ion at the center of a cube and CO minus ion at each corner. The unit cell of cesium chloride is, in that case, you've got the one in the middle, and you've got the ones on the corner, so that's a body-centered cubic. Okay, number 16, we're talking about cesium chloride again. And what it's asking is how many cesium ions it contains and how many chloride. In that case, it's one of each. So remember, each of those corner ones contribute 1/8. So 8 times an eighth is 1. And then the other one, whether the chloride is on the corner, so that's 8 times 1/8. And the cesium's in the middle, so that's a whole one sitting in there. So it's one of each. 17, what types of intermolecular forces exist between Cl2 and CCl4? The answer is dispersion forces. So in these, we don't have any hydrogen bonding. We don't have any dipoles. Why don't we have any dipoles? Isn't chlorine pretty electronegative? The reason is the symmetry of the molecules, so they kind of cancel each other out. So yeah, chlorine's electronegative. And so instead of CCl4, that was CCl3 H or something, then we would. But with the geometry of it, it cancels out. So we wind up with no dipole. 18, what happens to a polymer as it becomes more crystalline? Melting point decreases, density decreases, yield stress decreases, its stiffness decreases, or none of the above. Well, the answer is none of the above. Because when it becomes more crystalline, it becomes more ordered, you get more strength, you get some more of these properties. 19, the formation of a polymer. What type of polymer? Generally involves the elimination of a small molecule. That answer would be condensation. In condensation, that's the one where you pick out water. That's one of the more common ones, and that was the one we talked about in class a bit. Number 20. Which of the following lattices is one of the 7 primitive 3-dimensional lattices in which the relationship between the lattice vectors A, B, and C can be written A is not equal to B, not equal to C. So in other words, those lattice vectors have direction and they have size or length, however you want to think of that. And this is saying that the lengths are different, basically, of those sides. And for the choices that you had, monoclinic is the correct answer. 21, which has the lowest boiling point? So your choices are water and then some alkanes. And the answer is D, CH4 has the lowest boiling point. Anyone have a thought on why that is? So if we're talking about boiling points, we would say that the more intermolecular interaction you have, the higher the boiling point, right? Because you have to put more energy in to disrupt those interactions. And so in this case, we look at water and we know we've got dipole-dipole interaction, hydrogen bonding interaction. So that's going to be pretty strong. So we can rule that one out right away. Then it's just a matter of looking at these other compounds and figuring out, well, which of those, because they're all kind of the same thing, right? They're all just carbon and hydrogen. So we know there's no hydrogen bonding. We know there's no dipole type stuff going on. It's just those weaker intermolecular interactions. But remember what we said on that. The more of them that you have, the stronger it is. And so in this case, it's just the size of the molecule that determines that. Because what's the top one? Is that butane on top is going to be stronger because we've got 4 of those CH2 or 3 groups than just the methane down at the bottom. So that's why methane has the lowest one. 22. Molecular solids consist of atoms or molecules held together by, the answer is E. It could be dipole-dipole forces, it could be dispersion forces, it could be hydrogen bonds, it could be any of those. Number 23, a volatile liquid is one that is, the answer is E, it evaporates easily. And then 23, or rather 24, what portion of the volume of each atom or ion on the face of a unit cell is actually within the unit cell? My answer is a half. If you remember, it kind of cuts it in half there. And then finally, 25 is the other one of these calculate the total heat type problems. So let's go. Okay. So let's take a look at that. This is going to be similar to the other one we walked through, but go ahead and take a look at this again. So as I said, for me, I like to calculate the molecular weight. And so that's what I'm doing here, where I get the 187 number of carbons added to the number of chlorines, to the number of fluorines, using those atomic weight, getting that value. I got 35 grams of my compound. I'm going from liquid at 10 degrees to gas at 105. And so I'm also given my constants, my specific heat and delta H of vaporization. So I've got all the information I need. Now it's a matter of just breaking it up into those steps like we talked about before. The first step is going from 10 degrees to 47.6. That delta T is 37.6 degrees. So I take my grams, the 35 grams, times my constant of 0.91 joules per gram Kelvin. I have my temperature difference in Kelvin, and I do that math, and I get 1.198 kilojoules. Then I need to convert that liquid to gas. And so once again, I'm going to use my 35 grams. Now I need to change that into moles. And I do that by using my molecular weight, that 187 value that I calculated previously. I convert things to moles, and now my moles cancel, and I get left with a kilojoule value of 5.14. And then the third step is going from 47.6 degrees to 105 degrees. That's a delta T of 57.4. And similar to the calculation I did at the very beginning, 35 grams times that appropriate constant, and then now times 57.4, and I get a kilojoule value there. Then what I need to do finally is just add those three numbers up to get my final answer of 7.68. So once again, on these types of problems, some things that you're going to be doing. One is you're going to need to calculate a molecular weight, because you're going to need to convert something into moles at some point. So you need to do that. You need to make sure you have your constants, and that's usually given to you, or should be given to you. So you have your specific heats, and the specific heats are the joules per gram Kelvin values. Okay, and then in this case, we were vaporizing something, so we have the delta H of vaporization, and those constants, those delta H numbers are always going to be in kilojoules per mole, and that's where we use the mole calculation. And so it's a matter of picking the right one of those constants for whichever step you're looking at, and then thinking about what's going on. And usually it's something like you're getting to a temperature, so there's a temperature change, and then you change a phase. And then you go to another temperature, then you change a phase, and you go to another temperature. Kind of that common theme there. So, like I said, people did much better on this type of problem on the exam than they did on the quiz, so that was nice to see. And but if, like I said, if you still have some questions about it, you can always come talk to me, or just practice a little more, however you want to handle it. But there's a good chance it'll show up again at the end of the semester. Any questions about anything on the exam before we move on to the next chapter? Okay, give me a moment here and I'll pull up the slides and we'll start on solutions. Okay. So one thing I want to say before I start on this is to just remind everyone what we mean when we say solutions. Is that for me personally, when someone says I have a solution, I always think it's a liquid. Okay, and I think that's probably the way most people think about it. But if you recall, a while back, we actually said the definition of a solution, while usually we think of it as a liquid, it also can be gas. Okay. So just remember that, because we'll have some of the stuff that we talk about is talking about gases, and I don't want you to think, what the heck is he talking about? It's solutions, it should be liquid. Usually it's liquids, but gases by definition are solutions as well. So a solution is just defined as a homogeneous mixture of two or more pure substances. When I say homogeneous mixture, what does that mean? Does anybody know? Yes. Equal, yeah, it means it's equally dispersed. So if I have a homogeneous solution, if I sample that solution anywhere in it and analyze it, I should get the same answer of how much is in it, okay? Whereas a heterogeneous solution usually means you've got chunks in it, okay, if it's a liquid solution. So if if you're drinking a cup of coffee and you put some sugar in there and you stir it up, that sugar is going to dissolve and you'll have a homogeneous solution. It's not like if you stirred it up correctly, every time you drink it, it should taste the same, right? If you dump it in and you drink it immediately before it's dissolved, the first drink probably not going to taste any sugar, and then you get to the bottom, it's going to be real sweet, right? That would be drinking it when it's heterogeneous. So solution, we're just defining simply as a homogeneous mixture of two or more substances. In that mixture, the stuff that is in there in the smaller amount is the solute. The stuff that's in there in the greater amount is the solvent. So once again, if I take some sugar and put it in a glass of water, most of the molecules in that glass are going to be water molecules. So that would be the solvent. The sugar molecules, they'll dissolve for me, but there won't be as many of those molecules as the water molecules. So that would be the solute. So the ability to form solutions with substances depends on two things. One is what we call the natural tendency towards mixing. And I'll talk about what we mean on that in a little bit. But the main one, though, is the intermolecular forces. So you know all those intermolecular forces that you memorized and thought about for this last exam? They're still there for solutions, okay? Except it gets a little more complicated with solutions than it was with solids. But those forces don't change. It's just we have to evaluate them in more places than we did with the solids. That natural tendency towards mixing. So with gases, if you put one gas in a container and then add the second gas to the container, they will mix on their own. And that's because each of the gases want to fill up the container. Remember, that was, I think, one of the questions on the quiz or something. If you put a gas in there, or the gas goes and fills the whole thing. If it's a small container, it fills the whole container. A big container fills the whole container. You don't really do anything. That's just how it acts. Mixing of things causes more randomness for where the molecules are at. And randomness, some people call it chaos. In chemistry, there's a term for that. It's called entropy. So entropy is randomness or chaos, however you want to think of it. When you mix things, like in this case, two gases, we have oxygen and argon, we mix them up. It wants that entropy, it wants that chaos, and so you get mixing naturally because of that. The example I've heard people give a lot over the years about entropy is you have your desk that you're working at, and you have it nice and neat, and by the end of the day, it's a mess. That's chaos, that's entropy. Now, some people are better at that, keeping it neat and all that, but in general, most people, they start it out, it's pretty neat, and it gets more chaotic as time goes on. So that's how this is. So you can have instances where the chaos kind of overwhelms, or the entropy overwhelms it, and we'll talk about that a little bit more. The more common, though, is the attractions, okay? And I said it's a little more complicated than with the solids, and this is why. Is that if we're trying to figure out if something's going to go into solution, we have the solute-solute interactions. Remember, the solute is the lesser in concentration of the items that we're putting in. And so those molecules or those atoms are going to have some type of attraction, like we talked about before. Those interactions we have to overcome in order for those to disperse into the solution, right? Then there's also solvent-solvent interactions. So the solute wants to hang out with the other solute molecules. The solvent wants to hang out with the other solvent molecules. We got to break up those two interactions so that then we can have solvent-solute interactions. And that's what causes the mixing. That's what causes the dissolution. So whether something dissolves in a solvent depends on the magnitude of these three interactions, okay? And so we have to be able to overcome those solute-solute interactions, those solvent-solvent interactions, and then the solvent-solute interaction has to be favored, okay? So we gotta break up the first two, and then we gotta encourage the last one. And just to remind you again of what those forces are, those intermolecular forces, as I said before, they're the same ones we talked about the last couple of weeks with the solids, is that we have the dispersion forces, we have the dipole-dipole interactions, we have the hydrogen bonding interactions, which remember is a form of dipole interaction, and then we have the ion dipole interactions. So similar to what we talked about before in terms of that, the dispersion ones are the weakest, ion dipole and hydrogen bonding are the strongest. But these types of interactions are what's going on in each of these situations. That's what we're talking about for solute-solute. That's what we're talking about for solvent-solvent. That's what we're talking about for solvent-solute. So the good news is you don't have to learn a new interaction. The bad news is now you got to apply it to more situations to figure out what's going on. So one example is something called salvation. Not salvation, but salvation. And so the one that's most common is hydration, okay? And so hydration just basically means water is the solvent. And so in this case, we're looking at sodium chloride dissolved in water. And sodium chloride is salt, right? So over on the left here, we have a crystal of sodium chloride, nice crystal structure, tightly packed together, looks really nice. And then these little white and red things around it represent water molecules, where the red is an oxygen atom and the white is a hydrogen atom. And then in the sodium chloride crystal, the green ones are supposed to be chloride ions, and the bluish ones are sodium ions. So we put that into the water, and in order for it to dissolve, we've got to disrupt those interactions between the sodium and the chloride ions. We've got to disrupt the interactions between the water molecules. And then we've got to have more favorable energy to form what we see kind of blown up here in the middle of the water interacting with the chloride ion and the water interacting with the sodium ion. So if all those things happen, then the sodium chloride is going to dissolve. Well, we know sodium chloride is going to dissolve. We do that all the time, put sugar in, put salt in something and it dissolves pretty readily. Well, here's why. If we take a closer look at it, we see that the chloride ion, that's negatively charged, right? Well, water, when we talked about that before, we said that water is kind of nice because it forms these hydrogen bonds. And so we have the hydrogen, which has partial positive, the oxygen partial negative. So the hydrogen atoms will associate with the chloride negative charge. Remember, opposites attract on the charge. The opposite happens with the sodium ion that's positively charged. Now we see the red oxygens with that partial negative charge. That's what's interacting with the sodium. The end result is water can hydrate, which is what we call these water molecules around the atoms. it can hydrate both the chloride ions and the sodium ions, and that's this last picture here. It shows what the drawing of what the hydrated ions would look like in solution. So that general idea, you know, here we're looking at sodium chloride, but a similar thing would happen if you're looking at other things going into water. So, of course, we're going to be able to do calculations around this. I know everyone's excited about that and looking forward to that. But let's talk about what we're doing in that calculation. You can calculate a delta H for the solution as a whole. And that delta H is the sum of delta H of the solute plus delta H of the solvent plus delta H of the mixture. The delta H of the solute, that's the amount of energy it takes to disrupt those interactions of the solute molecules. So in the sodium chloride example, how much energy does it take to get sodium and chloride away from each other? That disrupting the solute interaction requires energy to go into it. So that's an endothermic process. Remember, energy going in, endothermic process. Endothermic processes are greater than zero, they're positive. And so that delta H of the solute will be a positive number. Delta H solvent is also endothermic for pretty much the same reasons. It's just a different molecule, but you're trying to disrupt that interaction between those molecules. And you do that by putting energy in. So delta H of the solvent also, that value will be greater than zero. So delta H solute, got to put energy in. Delta H solvent, got to put energy in. Delta H mixture. So for delta H mixture, that's the attractive interactions between the solute and solvent particles. So we could put energy in to get the solutes separated, put energy in to get the solvents molecules separated, but then we need there to be some attraction between these once they're separated, okay? That attraction then, that combining there, that's an exothermic process. So that delta H of the mix will be negative. So let me ask you this. We've got two numbers here that were going to be positive, the solute and the solvent. And then we got the mixed one, which is going to be negative. So our terms in our equation above, we're going to have a positive, positive, negative. For something to go into solution, what do you think we want delta H solution to be? Do you think we want it positive or negative? Any guesses? Parker, you want to raise your hand? I see it. It's twitching. Okay. Well, if what did I say I had to do to make this happen? The first one. I said delta H is going to be an endothermic process there. So if it's endothermic, what do I have to do? Put energy in. So if my delta H solution is positive, that would mean the whole thing is endothermic, right? So that would mean I had to put energy into it. If you take, if you're making Kool-Aid, for instance, do you heat that up? No, you don't. You just put the sugar in, you put the Kool-Aid mix in, you stir it a little bit, and boom, you're drinking your Kool-Aid, right? So you didn't put any energy in. So that can't be an endothermic process, right? Now, if you had to heat it up to get that Kool-Aid mix and the sugar to dissolve, then you would have been putting energy in, and it would have been an endothermic process, but it's not. So for this, what we want that delta H to wind up being negative, okay? Because if it's positive, then that means we had to put energy in, and sometimes you do that, and that's okay. But when I think of a real nice, easy to dissolve something, it's not me putting energy in. You heat it up when you think, gosh, this isn't going in fast enough or isn't going in easy enough. I'm going to put some energy in, I'm going to put some heat in. So what you want is, you want this delta H mix, that's a negative number, right? But you want that to be a big negative number relative to those, so that your delta H solution winds up negative. So here's kind of like the energy flow. This should look a little bit familiar because we kind of had some of these last chapter as well. But just to remind everyone what these diagrams are telling us, these lines going up, so we have delta H of the solvent going up, delta H of the solute, and we see this is telling us that's the energy we had to put in to interrupt those intermolecular attractions of the solvent and the solute. So energy is going up. That's the endothermic, right? And then once we get all this done, we have this total here of the energy of those two steps. Now we're at this higher energy level. Then the mixing, that delta H in this case goes way down. That's the red line going down. And we see that it goes down more than what the initial energy value was, okay? So we have this red line going down is greater than the two lines going up combined. So that tells us that we have a negative value for that final delta H value. So that would be that delta H of the mixed solution. That's an exothermic process. The one on the right, similar type of diagram, but the difference there is our delta H from the mix doesn't go down as far. And so there's a gap between where it goes down to the initial. That tells us that delta H is going to be greater than 0. It's a positive value. And it's an endothermic process to get that to happen. For that endothermic process to occur, we would have to then put that energy level in order to make that happen. The exothermic one, we call that those happen spontaneously. Spontaneous to me is kind of a dramatic word. I just look at it as it goes into solution. One disclaimer here. When you do these kind of calculations, if you get kind of close to being an exotherm, but you're not quite there, that's where the randomness, the entropy thing kicks in. And so there are examples of things that technically aren't exotherms, but they go into solution because of the entropy of things liking that randomness. I wouldn't worry about that too much. We're not going to, those are more the exceptions than the rule. But I did just want to mention that does happen. And entropy does play a role. To me, the entropy plays more of a role in the gases than the liquids, but it does happen sometimes. The other thing I want to mention is just because something goes into solution doesn't mean that it dissolved, okay? It may have reacted. So if I say something dissolved, so once again, taking sugar into water, so if I take a spoonful of sugar, put it in a glass of water, stir it up, and it dissolves, if I analyze what was in that solution, it would still be that sugar molecule, okay? The molecule didn't change. All it changed was those intermolecular forces, which now allowed it to go from being a solid to being in the liquid phase. If I do a chemical reaction, then something is changed on that molecule, okay? So, and then whatever is the resultant is now soluble. So when things go into solution, and here we have an example of where they have nickel metal and hydrochloric acid. They put the nickel into the hydrochloric acid, and what happens there is the hydrochloric acid and nickel react together, and you actually form nickel chloride, and then you'll get some hydrogen gas involved. But let's focus on the nickel chloride. So now you get this kind of greenish, yellowish solution. Well, that's not, in this case, that's not nickel dissolving. You've changed the composition. And instead of being just nickel, now it's nickel chloride, not just nickel metal. And actually, you could do some things to precipitate it out and then see that. And certainly you would agree that this material this kind of greenish material on the right is very different than the little metal beads on the left. Further evidence that you've changed what it is. So, like I said, put some sugar in water, dissolve the sugar, you haven't changed the sugar molecule. Sometimes though, when you mix things together, you get a chemical reaction where you actually change what it is that you put in, and now it's something else. Okay, any questions about any of that stuff so far? All right. So as you put that solid in and it starts to dissolve, you have all these concentration changes that are happening, okay? And so as you get more stuff dissolving into solution, there's a greater chance that those molecules, because it's more concentrated, can collide and run into each other. When that happens, you can have it go back the other way. So we have solvent, we put it together, it starts to dissolve in the solution. As the solution gets more concentrated, you can have instances where these molecules kind of run into each other, and then it goes back and it does what we call crystallizes, and you get solids appearing again, okay? So there's a whole branch of chemistry where people study crystals and crystallization and those kind of reactions. This is kind of what's going on. When you get to where this process is equal, then if you add more solute, it doesn't dissolve, okay, unless something comes out. And when you've gotten in the maximum amount of solution, or rather solute that will fit into the solution, that's called a saturated solution. So in other words, if you get to the point where if you add any more, you'll start getting crystals. That's a saturated solution. When you're below that concentration, it's an unsaturated solution. So if you ever look up solubility data for compounds, there's always, you know, some amount per volume at a certain temperature is what the data will tell you. What that tells you is that's the maximum amount of stuff that you can get to go into solution before it starts precipitating out. This putting stuff into solution, the maximum amount, that, as I said, that's known as the solubility of the material. And so if you've ever been mixing something up and you put it in the beginning and it goes into solution, so you add a little bit more and add a little bit more and it keeps going into solution, and now suddenly it doesn't go into solution anymore, you've reached its solubility limit. So once again, if you take the Kool-Aid example, it tells you a certain amount of sugar to put in there. If you decide you're going to put twice as much sugar, it may not go into there. You may reach its solubility limit in the water. And then what that means is you're just going to have some sugar sitting at the bottom, but that doesn't mean a whole bunch hasn't gone into solution. It's just you've reached that solubility limit. There is another thing that can happen, and I'm just going to briefly mention it just so that you've at least heard about it, but don't get too worried about this, is that there's saturated solutions and unsaturated solutions. Like I said, saturated is you've added as much as solute in that the solvent can handle and have it go into solution. Unsaturated just means all the concentration is less than that. There's also something called supersaturated solutions. And so there's certain things you can do to kind of trick the solubility where you can actually get more material in than the solubility limit says you can have. The issue with that is it's unstable. And so it doesn't take much to then suddenly get stuff crashing out, precipitating out. And it can range from things of a speck of dust gets into your solution, and then that'll serve as a seed to get it to precipitate out. Sometimes people will just take a spatula and scratch the side of the beaker to get a fresh surface, and you can get some crystallization that way. There's a host of things you can do. Like I said, don't worry about this too much, but I do want you to understand that you may hear some people talk about supersaturated solutions. One way that people supersaturate is they'll increase the temperature a lot because solubility increases as you increase the temperature, then they'll cool it down. And sometimes if you do that slowly enough, it'll stay in solution for a while. But to be honest, eventually it usually crashes out. So the ones I want you to really focus on though are saturated and unsaturated. Saturated being where you reach that maximum solubility, and unsaturated is concentrations less than that. Supersaturated is kind of a fun thing to think about, but to be honest, it's not the norm of that thing that you do. Okay, when we talk about factors that affect solubility, we have that solute-solvent interaction. So that's those interactions we were talking about before. For gases, for gaseous solutes, so putting gas in the solution, pressure is a big deal. That makes a difference. And then the other one, like I said just a moment ago, temperature affects solubility also. So we're going to talk about these a little bit here. So solute-solvent interactions. You know, after Gen Chem this year, there's a bunch of things I hope you remember. But if you're only going to remember two things about Gen Chem, they are for charges, opposites attract. Okay, we talk about the positive charge, negative charge, opposites attract. The other one I want you to remember is for solvent type stuff, dissolving things, like dissolves like. Okay, those are two things I hope you go for the rest of your career remembering. And when we say like dissolves like with solutions, and we're talking liquid solutions now, we're basically talking about polar stuff dissolves polar stuff, and non-polar stuff dissolves non-polar stuff. One example I like to use is if you ever cook, say, like a hamburger or some kind of piece of meat at home, and you cook it in a frying pan, and then you let it sit there for a while. You don't clean it up right away. What do you usually have? You usually have kind of a greasy feel to it that's sitting there. Well, that's grease, of course. That's the fat, that's the grease. And have you ever then taken that pan after that's kind of cooled down and put water in it? What happens? Nothing, right? The grease doesn't mix with the water. You can just pour the water off and then the grease is still sitting there. If you take a rag or a towel or paper towel or something, kind of trying to clean it up with the water, what does it do? It just smears the grease. It doesn't. The grease is very non-polar. The water is very polar. So like dissolves like, polar water, non-polar grease, it's not going to dissolve. You can let it sit there for a week. It's not going to dissolve. But you think about it, now they sell some products that are chemicals that you just spray on there, and you let it sit for 15, 20 minutes, and you can just take a paper towel, wipe it off, and it's all clean. Well, I guarantee you that those are compounds that are non-polar. And that's the like dissolves like. So what I like about that is, you know, I spill something on my shirt, which happens more than I care to admit, and I don't want to have a big stain or throw away my shirt. I think about, well, what did I spill? If it's something greasy, then I need to go get one of those stain stick kind of things, which has non-polar stuff to get it out. If it's my Kool-Aid that I was drinking, well, that's polar. I know. Why do I know it's polar? Well, it dissolved in water easily. So I'll just go over to the sink and run some water on it, and it's going to be good. It'll wash it out. So I love the like dissolves like because, first of all, I tell my family this all the time, and they get aggravated with me, which is fun. But the nice thing is it's just a nice practical thing. So like I said, opposites attract on the charge, like dissolves like on this stuff. If you don't remember anything else out of this class, please remember those two things. Hopefully you remember more than that, but okay, so when we talk about solute-solvent interactions, the stronger that interaction, the greater the solubility in the solid. When we talk about gases, they only exhibit the dispersion force. So the larger the gas, the more soluble it'll be in the water. And so here's just a table that shows solubility of these different gases in water. And we see that it goes up as the molar mass increases. That's not as exciting as light dissolves light. Let's talk a little bit more about this light dissolves light thing and have a couple examples here. So when we talk about organic molecules, and when we say organic molecules, an organic molecule is just something that has carbon in it, okay? So in this case, we've got cyclohexane up here on the top right. We've got glucose down on the bottom right. So these are both organic molecules. Remember we talked about water can do hydrogen bonding because we've got that oxygen and the two hydrogens off of it. And so water is a very polar molecule. Hydrogen bonding is just another way of saying it's polar. You've got those dipoles. If we look at these two compounds here on the right, the top one, the cyclohexane, what do we normally need to have something that's polar? So for hydrogen bonding, what did we say we had to have? We had to have oxygen, right? That hydrogen bonded to an oxygen, or the hydrogen bonded to a nitrogen. We said fluorine also, and that's fine, but the real ones that do hydrogen bonding is typically the OH, the NH, those are the ones that are the ones. The fluorine is also, but that's less common. Do you see any of that up here on the cyclohexane? All you see a bunch of hydrogens, but they're not bonded to the right thing. They're bonded to carbon. So there's no dipole there. Down at the bottom here, at the glucose, the sugar molecule, we've got an OH here, 2, 3, 4, 5 OH groups. We've even got an oxygen here in the ring, but we've got 5 places there where we can have hydrogen bonding. So that's really polar, right? So if I was going to pick glucose or cyclohexane, and we were going to make a bet on which one will more readily go into solution for water, which one would you bet on? How many of you would pick cyclohexane? Anybody? No one? How many would pick the glucose? Okay. How about on Zoom? Anybody pick cyclohexane? I'll take that as a no. The reason is the cyclohexane is non-polar. The glucose is polar. You have the hydrogen bonding on the glucose. So that's going to go into solution, whereas the cyclohexane is not going to be soluble. That's the like dissolves like. Water is a polar molecule, so it's going to dissolve other polar molecules. So when we mix things, and they mix, no matter what the proportions are, we say that those liquids are miscible together. If we mix them together and they don't mix, we say they're immiscible. And here we have an example of hexane, not cyclohexane. This is the straight chain hexane, but hexane and water. And what, if you can see in this Erlenmeyer flask here, on the top here, this is hexane. Then you kind of see a line there, and after that, and then below the line, that's the water. So what this is that you took some hexane and you took some water and you mixed them together and you shook them, and you shook them and you shook them and shook them, and then let it sit. They will separate themselves like this, okay? And then the hexane would be on top and the water would be on bottom. Anyone have an idea of why hexane's on top? What does that mean? Yes.
It's not polar.
It's non-polar, but what else why is it on the bottom? You still get a separation, but the water would be on top and the hexane would be on bottom.
Is it way less?
density. Remember, density is mass per volume, and hexane's density is less than water's density. That's why the hexane's on top. So hexane water, this mixture, is used all the time in chemistry to do something called an extraction. So if you have a sample that has polar compounds in it and non-polar compounds in it, and you want to separate the polar from the non-polar, what you'll do is you'll take some hexane and you'll take some water, you'll add them together, and you put the solution in it as you're trying to separate those molecules. You shake it up for a while. There's something called a separation funnel that people use where you can then, it has a spigot on the bottom and you can drain off the water and have that phase. Then you can drain off the hexane and have that phase. And then you can analyze those and see which is in which. So the fact that things are miscible, your first thought is, well, that's terrible. I got two phases. Sometimes it's useful, especially when you do like an extraction to isolate certain material. The other example of this kind of immiscible thing is if you ever have vinegar and oil salad dressing, okay? So the vinegar is essentially the aqueous phase. You have some acetic acid in there and you have water. And then the oil is whatever type of oil you're using, but those tend to be non-polar. You know, you could shake that stuff and shake that, and it's always a race to get it poured on your salad before it really separates badly. You only get one or the other, right? So that's kind of the other example that most people are familiar with from just a normal life type situation. So I do want to point out another example of this kind of thing that's more of a biology focus on it, of solubility. And so if we look at vitamins, so vitamin A is this one over here on the left. We have the structure for vitamin A. And on the right, we have the structure for vitamin C. If we look at the vitamin A structure, we see a long chain of carbons and hydrogens on the left here, when we see one OH group on the right. So that OH group is going to be polar, but it's just one little group compared to all this other stuff that's not going to be very friendly with water. We look at vitamin C on the right, and we've got 1, 2, 3, 4 OH groups. And we've got some other things, but that's not really that big in terms of the amount of the molecule. So what it tells us is that vitamin C has a lot of opportunity to interact with water, like dissolves like, a lot of polar stuff. Whereas the vitamin A just has this little bit, but most of it is non-polar. What that means is, remember we talked about like cooking hamburgers or whatever, and the fat being non-polar? Well, fat is fat, it's non-polar, and so that means vitamin A is a fat-soluble vitamin. So it means that vitamin A in your body will go and can be stored in your fat. So fat isn't bad, it's a good thing to store things like vitamin A. And so in that fatty tissue in your body, you'll have the vitamin A stored. Vitamin C won't be stored, it's too polar. It won't solubilize in that fat matrix. And so that's why with vitamin C, you know, some people take it every day who are concerned about that in a vitamin or some type of supplement, or they drink orange juice every day or something like that. That's because it doesn't get stored in your body because of this solubility thing. Whereas vitamin A, that's less of an issue because as long as you're eating it, if you don't eat it every day, you're storing some extra and then your body still has it. So this is for all the biology majors out there. I'm sure you'll hear more about this in better detail than I can provide from your biology teachers. Okay, any questions about the solubility stuff, the like dissolves like? Okay, like I said, that's really a big deal in the world of chemistry and also just in general. It's real big in laundry, as you heard from my examples too. So, okay, let's talk about pressure a little bit. So if we're talking about pressure, what we're really talking about is gas solubility. So solids and liquids, they're really not affected that much by pressure in terms of solubility. Gas solubility is affected by pressure. And there's actually something called Henry's law, which kind of explains this. And what Henry's law tells us is that the solubility of a gas is proportional to the partial pressure of the gas above the solution. What this means is you increase the pressure, you increase the solubility of the gas into the solution. And it's demonstrated below here with this piston example. So here in the first example, we have some carbon dioxide gas introduced into this. We establish an equilibrium between the gas phase and the liquid phase at whatever pressure that is. If we push that piston down, then that's increasing the pressure on the system. And what that does is that drives more CO2 molecules to dissolve into the water, or whatever the liquid is. I'm saying it's water. And then that will increase the concentration in the solution. And then after a period of time, you'll have that equilibrium will happen. And so equilibrium just means you have the same amount going in as going out, and so you reach that steady state. Over here on the right-hand side, we have a graph of some common gases, oxygen, CO, N2, helium. And what you see is that the solubility varies based on the gas, but what you do see is consistent is that as the pressure increases, so here partial pressure is increasing, the solubility increases, okay? So the solubility number will vary based on gas, but the general trend of increased pressure, increased solubility holds up. And that's what our Henry's law is telling us. The other thing that affects solubility is temperature. So if we're talking about solids, almost always, as you increase the temperature of the solution, the solubility increases. There are some exceptions to that. We're not going to worry about the exceptions because most of the time, almost every time, you increase the temperature and the solids go into solution better. They go in faster. Sometimes you can form one of those supersaturated solutions that we talked about before. You can get a little extra in, but they do. And if you don't believe that, you can do a simple experiment of take a glass of water and put sugar in it and stir it to get it to dissolve and time that, and then take a glass of hot water and then do the same thing. And it'll go in much quicker in the hot water than in the room temp water. And so that holds true for almost everything. This graph over here on the right shows you that there are a couple exceptions, but what you normally see is a pretty big difference on these. As they increase the temperature, they go up. You get something once in a while like this sodium chloride that doesn't have a lot of impact, but part of that is salt goes into water pretty easily anyway. So there's not a big gain on that. But for the most part, most of them are like these others that show a pretty sharp increase in solubility as you increase the temperature. Gases, just the opposite, okay? So with gases, the solubility decreases as the temperature increases. And the example that we have here is saying that cold water, in this case rivers, have more oxygen content than warm rivers. The example I like is if you know anyone who's got a small pond, okay, and maybe they have some fish in there and they fish a little bit, you'll see a lot of these small ponds have some type of like bubbler in the middle. That's because in the summer when it gets super hot, there's not a lot of water there, and this happens. The oxygen, as the temperature gets hot, leaves the water, and there's not enough oxygen in there, and you can get the fish die. You don't want that in your fishing pond. So that's why they'll have those bubbler things in there to give them enough oxygen. And so if it's a solid you're trying to dissolve, increased temperature, good thing, makes it go in better. If it's a gas you're trying to get into there, That's actually the opposite. The solubility decreases as you get your temperature higher. Okay, there are some homework problems associated with this. Take a look at it. And any questions about anything I've talked about so far? Okay. Up until now, we've been talking from a qualitative perspective. Light dissolves light, intermolecular forces, stuff like that. At some point, we want to actually add numbers to this stuff. And so what we're going to do next is we're going to talk about how we express the concentrations. Some of the stuff I think we've talked about already, and some of the other stuff might be a little different. But we'll go through them all just so that if it's something new, you learn it. If it's not something new, it's a refresher. And the typical units of concentration are mass percentage, parts per million, usually referred to as ppm, parts per billion, ppb, mole fraction, molarity, molality. Mass percentage is fairly common. ppm and ppb are extremely common. And molarity, you've been using already. So hopefully you know that one. That's real common. Mole fraction is, people use that some. Molality, I think biologists like that. I don't think chemists hardly ever use that, to be honest. But we'll go through all of these so you understand the definitions and how you would use them. For me personally, I probably spend most of my time with ppms. That's the most common one I use. Okay, so mass percentage. If we say we're asking for a percentage of something, that just means out of 100. So it basically means you take your answer and you multiply it by 100. So whether it's percent whatever, you do that calculation and then you multiply it by 100. And what it is the ratio of the mass, in this case, the mass of the solute to the total mass of the solution, okay? So we'll have an example of that in a moment. So mass of the solute, basically, divided by the mass of the solute plus the solvent, that total solution, and then multiply that by 100. Here's an example of that. So if we were going to make a solution, and we did it by taking 13.5 grams of glucose and dissolving it in 0.1 kilograms of water, what would be the mass percentage of this? So we would start out by saying this is mass of glucose divided by mass of solution. So our mass of glucose was 13.5 grams. The mass of the solution is the mass of glucose, which is 13.5 grams, plus the mass of water, which is 0.1 kilograms. But we're working in grams, so we don't want to express the water in kilograms, we want to express it in grams. So to do that, we move the decimal place over to the right 3 places, because 1,000 grams equals 1 kilogram. And so now we know our total is 13.5 grams from the glucose, plus 100 grams from the water. And then we multiply this ratio by 100 because we want it expressed as percentage. Okay, parts per million and parts per billion is essentially the same calculation, except what we're multiplying it by in the end. Okay, for part per million, that's 1 in a million. 10 to the 6th is what we're multiplying. Remember, for percent, which is 1 in 100, it was times 100 for 10 to the 2nd. Here, 1 in a million, we're multiplying it by a million, so 10 to the 6th. For part per billion, we'd be multiplying it by 10 to the 9th, a billion. So it literally means 1 in a million, 1 in a billion, type thing. So, but in terms of what we're doing is we have mass of that component, mass of that solute, divided by total mass of solution. Exactly the same thing we did with weight percent, except now we're expressing it in ppm or ppb. These are the calculations you use when you're doing really, really dilute solution stuff. So if you ever look at like environmental data or anything like that, it's going to be in something along the lines of this. Weight percent data would be more like if you look at the percentages in a product. Let's do this example, and this will wrap up for today. So this is an example of how you calculate ppm. So if you had a 2.5 gram sample of groundwater, and you said that you found 5.4 micrograms of zinc plus 2 in there, what's the concentration of zinc plus 2 on a parts per million basis? Well, we need to remember that microgram is 10 to the minus 6 grams. Remember that prefix, that micro prefix is 10 to the minus 6. So then if we go and say our mass of our solute divided by the mass of solution, we said this was 5.4 micrograms. So to express it in grams, it's 5.4 times 10 to the minus 6 grams. That's from our conversion here, 1 microgram is 10 to the minus 6 grams. Then we divide it by 2.5 grams, that was our total weight of our sample. We do that math, and then because we want part per million, we multiply it by 10 to the 6th, and it tells us that we have 2.2 part per million zinc plus 2 in that water sample. Okay, any questions about this or weight percent? All right, that'll be it for today, and have a nice weekend. I'll see you on Tuesday.